Okay, good afternoon, everyone. Shall we start? I guess most of you know me, so no intros. I'm quickly going to go through the grading related details and stuff like that, and then dive into the introductory material. My office hours: Wednesdays 2 to 3, and Fridays 1 to 2. I'll have occasional travel, in which case I'm going to schedule uh, as Monday as the backup day. So I'll let you know. Um, so what this course is about, many of you are familiar faces from my previous 202A. So those of you who took the embedded systems 202A, it was focused largely on the time dimension of embedded systems. So making things real time, meeting latency requirements, things like that. This course is largely focused on the other major physical variable that affects embedded systems, or more generally computing systems, and that's power slash energy. So the focus of this course is going to be on how to manage the energy that is consumed by a system and related issues like battery life and things like that. So we'll see as the course progresses that there are a variety of reasons why power and energy matter. And the focus here is really looking at computing systems and cyber physical systems in their totality, and kind of then worrying about issues of energy. We'll look at to manage energy at the system level. You have to understand where energy is consumed, how it is produced, etc. And therefore, we'll look at the whole chain or the whole energy pathway, and we'll look at managing energy for a variety of purposes. Most common one which we encounter is just the battery life in our smaller devices like smartphones and all, but there are other reasons as well. Things heat up. When they heat up, all sort of bad things happen, including failures and all. So thermal management becomes an issue. In many cases, the peak power, namely the peak current that you are drawing from the battery or the energy supply, often is the constraining thing. It affects cost, for example. Energy itself obviously has cost. And finally, there's just the issue of sustainability, which is kind of the global warming and air quality and those kind of issues. So depending upon the kind of system you're looking for, these different dimensions matter. What we'll do in the course is to really kind of look at, maybe in the first 2/3 of the course, look at computing systems very broadly. So computing, communication, these kind of systems. And the latter 1/3, we are going to look at other systems such as buildings, EVs, grids, mostly buildings, but sort of idea being that we begin to look at those systems where computing has become very important in making them more energy efficient. In a sense, two halves to it then: making our computers green or energy efficient or low power, and then using computing or computational intelligence to make other systems green and also. So that's kind of the two themes that I hope to capture in the course. We are going to look at kind of the whole gamut of things: software, hardware, algorithms, as we go along. What I'll not cover are kind of really the lowest physical layer behind this thing. So we'll get some abstract view of this, but this course is not really on making more energy efficient transistors or better battery chemistries and all. So we're not going to really look at that. And likewise, this is a topic, unlike time, which we previously focused in 202A, power does have lots of socio-political implications as well, and a lot of these things are surrounded by those kind of debates. There are also issues of that I can make a system, a building or a data center very efficient, but at the cost of making rest of the society suffer. So there are also these other trade-offs which occur. Again, we are going to mostly gloss over those as well. Course is intended to be self-contained, so if you have not taken 202A, shouldn't really impact. What I'm really expecting is that you will have a good sort of computer engineering type undergrad background, and of course the ability to pick up learn material as we go along, because again, as you can imagine, topic like this kind of spans so many layers of the system that I cannot meaningfully have a specific course as a prerequisite. You have already received emails from me, so as you'll see, one of the things I'm planning to do is to have students present papers in the class, and that unfortunately does mean is I have to limit the enrollment, and the other reason I have to limit the enrollment also is to be able to support the projects. So I'm going to let in 25 students in the class. I handed out 25 PTEs. I'm going to keep track of them through some mechanism and hand out a few more if I have some slots open up, but it's kind of a hard limit because I have to the limited resources lecture time, so I have to accommodate sort of both aspects. Just one request: if you do decide to drop the course, do it soon. And the second thing is also officially drop it. Don't just stop attending it, because otherwise I don't have an easy way of knowing. One really thing I emphasize every time, which is UCLA does allow you to drop the course until the last day of the 10th week of the classes. Unfortunately, it creates a lot of problems. For example, last time my 202A, I had one student drop out in 9th week or so, leaving the partner in a lurch because the homework was joint homework, as some of you might recall, and likewise one group dropped at the very end. So it doesn't so much hurt me as it hurts your peers, your colleagues. So I think just because you can avail, don't kind of misuse that flexibility. Sometimes there are valid reasons, obviously, but please try not to. If you are taking the EEMS comprehensive examination, so since we don't have a final exam and all, I basically use the course grade as the grade for your comprehensive exam purposes. So just wanted to make that clear. Your overall grade is what will matter, and that's what the department will use. The grading structure, I will have some homeworks which are combination of problem solving, programming, simulation. I'll have paper summaries and presentations. So the way it's going to work is the following. Each one of you will have to present a paper, which basically means that you'll have to give a talk on that paper, prepare slides. I budgeted 17.5 minutes. Don't ask how I came up with that precise number. But then the idea is that every student in the class has to submit a review / critique of the paper. I'll describe that in more detail, but it's roughly along the lines of those of you who have taken EE 297 EE seminar, what I asked you to do, or I'm asking you to do this quarter if you're taking. It's very similar in style, but in this case it's going to be in the form of 4 slides. And kind of the idea is that after the student has presented, which you will know well in advance because I'm going to set out the list of papers, so your assignment would be known in advance, but what will not be known is that which student is selected to lead the discussion on the paper. So that would be random, and if you are absent, you get a 0 on that, and I'll move on to the other student. Okay, so if you're going to be absent in a particular class for some valid reason, again, make sure to make me aware. And then finally, the course project. Again, individual or teams, analysis, design, experimentation. Again, I'll be offering some project ideas. So this is kind of the grading split. Any questions? Okay. Again, I may have some minor deviations from this, hopefully not. Research paper presentations, I think I already described. So I'll basically have a list of papers. The idea is that this is again a relatively fast moving field. The whole concept of making computers energy efficient, while it's been around for a while, there continues to be lots and lots of current activity that's happening. So for a lot of topics that we are going to cover, I'll pick up something from the recent literature. These are going to be longish papers. Okay, so these are not your 3-4 page workshop type papers, but they are journal length papers typically. You'll have to present once in the course, and very occasionally, if the paper is really hard or long, I might make it a team presentation, but most of them, probably all of them, will be one student, one paper. Um, so the idea, you'll have to prepare a talk. You can the idea is the slide should be based upon your original reading, but you are certainly welcome to scavenge the web or approach the authors for original slides as well and incorporate them. But anything which is not your own, you have to acknowledge it. But kind of really, ultimately, it's a talk. Think of it like it's a talk that you are preparing, but leveraging material that you cite from elsewhere. I expect participation by everyone, so roughly half the score for this is budgeted for the summaries and Q&A session, and half for the actual the one presentation that you would do. So we'll start on this thing, should say, starting Monday of week 3, but I still have to kind of budget out a schedule, but week 3, maybe week 4, we'll kind of work on that. So 50% of the score on the presentations and 50% on the summaries / Q&A. Let's see, course project. Essentially, the idea is to explore something related, but on your own. You really, as usual, again, those of you who are in my 202A, I often have one of my student or postdoc mentor you. I still have to come up with the topics out here, but oftentimes, for example, people have done things around smartphones or batteries or things like that because they are much more accessible to do. We also have had projects which have involved buildings kind of stuff. Nowadays, if electric vehicles and all are another sort of area where interesting things can be done. A lot of projects can often tend to be on analyzing data. So there are data sets available on the web, and you pick something up and analyze those, or simulation oriented things. Oftentimes doing implementation in this domain tends to be tricky, particularly if you are doing stuff with buildings and all. So I'm open to all sort of ideas. So start thinking. Energy is something that you encounter on a kind of day-to-day basis. Certainly, our phones running out of batteries and other such devices. So there are lots of possibilities there. Project timeline, again, week 3, I'm hoping that you would have the team finalized and kind of a project abstract done. The way it will work is that your project, you'll create a website for your project, which is kind of both a running journal as well as the end product, the final report, and you'll update it every week. I'll provide some guidance on that, and then you will make a presentation / demo in the last week. If necessary, we could do it in a recorded manner, but I'm hoping that we can all do it in person. So you'll do it in my lab, one-on-one with me, basically. So that's the project part. The way the project grade is split up, so remember 45% for the overall project, so 25% for kind of the actual work done. And I do want you to take challenging things. Okay, so essentially I do normalize it for kind of what you started at doing. If you pick a very doable project or something which has been done and all, and then not perform on it, versus if you take something hard and then have to back off, those are very two different things. We'll also 10% for the final presentation demo and 10% for the project website report. So this is 10% of the course, 10% of the course and 25% of the course. Let's see, any questions on this? Some more guidance out here which you can read on your own, but main thrust is the following. Try to do something new and don't reinvent the thing. So idea behind these projects is not to redo stuff which has already been done, but do something new and leverage stuff which is already out there. So there is no problem in reusing software or data or stuff like that which already exists, as long as, again, you disclose such usage. You can work in teams of, I think usually teams of 2 work out well, but many of you might want to work solo, for example, if you're not on campus enough. Teams of 3 for particularly ambitious projects as well. One thing which I would like to do this time around, because I think last quarter I didn't ask for it and didn't work very well. At the end, I would like each person individually and separately to submit to me what they and their teammates did. Okay, because I don't want to end up having to resolve fights and stuff like that. And at the same time, when presentations happen, I see a very distinct difference in some of the teams. And it was clear that one member kind of did bulk of the work. So I want each one of you. So that's one individual thing that you'll have to do for the project, which is describe what you did versus what your partners did, and hopefully you would discuss and reach on a consensus on what you are submitting. Because I do want to reward. So your project grade across the team may not be the same, okay, depending upon the contributions that happen. Because I do want everyone to kind of pull in their weight. We'll primarily use Piazza. Many courses are using it. I have used it if you were in my previous courses. So you should have received an email from me. I gave you a PTE. If not, the URLs are out here, but just go on piazza.com and search for this course. No textbook, and we'll obviously have that set of papers. They're all online, so I'll just give you the URLs. There are courses elsewhere. I guess among the current courses, probably the one at CMU, the very first bullet is the most closely related by a close friend of mine. So we exchanged notes and all. And then there are a bunch of sort of older courses, and there are a bunch of conferences and journals. This is a topic where you'll find papers both in routine journals. So if you look at, for example, major conferences in computer architecture and stuff, operating systems and mobile computing and all, a big theme obviously always is that of power. But that apart, there are also conferences and journals which are dedicated to the theme of power. So there, it's much more so than speed. Power is such a dominating consideration that a good fraction of papers in general conferences tend to be around this theme one way or the other. There are also a bunch of standard bodies, technical bodies, government agencies and all, which are in this space. There's a whole IEEE technical area, which is kind of collection of individuals who come together, create conferences and journals and stuff like that, as well as agencies. So Energy Star rating, which we kind of see in many products and all, are a result of that. Cheating plagiarism, you can read, but bottom line is any work that you represent as your own should genuinely be your own. Things that I assign to be done individually should be done individually. Things where you can work in a team, you should work in a team. It's perfectly okay to use Piazza and all to kind of help clarify a question and all, but ultimately when you submit something, it should be your own work. Let's say I hand out a homework, it's perfectly fine to discuss what the question may mean, what might be possible approaches, but you then still have to do the work, and you should do it on Piazza. I leave the anonymous posting thing enabled on Piazza, so you can post anonymously as long as there's no misuse. I will retain that. And finally, on the logistic front, so as of now, I think I have only one date, which happens to be just fairly soon, that I'm going to miss due to travel. That's Wednesday, January 25th. Inevitably, there are one or two others as a quarter rolls around. The 25th one is falling a little bit too early, so I might not have a makeup for this one. I'll probably do a recorded lecture, but for future ones, I will arrange for a makeup by some guest speaker. But even for this one, I might, so don't assume as of now, don't make any other plans yet until I finalize it. So that's on the logistics side. Any questions, clarifications, anything? How many of you are here and do not have a PTE number? Good fraction. Okay. So those of you who do have a PTE, if you do not enroll by end of today, I'll assume you don't wish to enroll, in which case even if you enroll, I'll have Diana kick you out and hand your PTE to others. So I'm probably going to do another round of email polling to see what PT numbers are going to be free. And so those of you who are seeking PT, I would say just bear with me for perhaps this week, and hopefully things will come out. If you have a particularly compelling case to make, so roughly speaking, this is what I had done. I gave priority to PhD students and computer science students. I'll clarify both of them. PhD students because this is an advanced course, and computer science students because I do want the CS perspective to be well represented in this class. And as you know, this cross-listed course. And after that, I went by the case you made. I wanted a well-balanced background, so I kind of looked at the kind of prior background you had and tried to shape the class. Having said that, the process obviously is very subjective, but if you have a particularly compelling case to make, like for example, maybe you are graduating after this quarter or something like that, come and talk with me. I'll sort of see or make sure that your form submission had it. But anyway, towards the end of the week, I'll again go through this and allocate more more PTs if I can. You had a question? Nope. Okay. Cool. So let's move on then. If no questions. One other thing, as you notice, recording the lecture, so I'll put up on YouTube. Hopefully this quarter I'll be more diligent about actually doing the conversion and putting them up, but they're all getting recorded. Okay, so rest of today's class, we are basically going to do a broad brush view on what are the set of topics that we are kind of going to touch upon, and also some of the usual motivational things and all. And I feel free to ask questions and all along the way. I really want this to be an interactive class as much as possible. One thing I find always puzzling is that my undergraduate class, the students ask me a lot more questions, and my graduate class are utterly silent. Hopefully you guys have proved me wrong, so let's hope that. Okay, so what this is about is what kind of energy related challenges exist broadly in information technology sort of space, and what kind of opportunities have emerged in recent years that people have been pursuing. Anyway, so energy, this is some funky quote. What does it say? Energy permits things to exist, information to behave purposefully. I think the thing that we are seeing currently in many cases is the convergence of energy and information. Both ways, that is, our information systems are a big culprit in terms of energy consumption. Anyone knows how much of planetary energy consumption goes to data centers, information technology, data centers, let's say, because they're often sort of quoted as ballpark guess? Yeah, you're pretty close, 6-7% in that range. Okay, they are bigger than the airline industry at this stage. Okay, in terms of the footprint, and so as you might imagine, every time you play a YouTube movie or do a Google search or whatever, you basically are consuming energy. Now, offloading this way into the cloud shifts the energy consumption right away from your end devices to things in the cloud, but nevertheless it is there. And a lot of people have studied things like relative energy efficiency of doing things locally, doing things in the cloud, electronic delivery versus physical delivery. Are you better off having a Netflix ship the DVD to you versus you are streaming the movie, in which case there is energy consumption happening out in the cloud, all those kind of issues sort of, so there's kind of an nexus between these two things. And the other part is that when it comes to managing energy, then computation is what makes energy management smart. So even trivial things like instead of a static solar panel, have the solar panel track the movement of the sun, or predicting changes in wind pattern in a geographical region and then adapting your grid to that so that you can activate or deactivate fossil fuel based generators accordingly, or stuff like that. So as you can imagine, smartness makes better energy management, and smartness comes from computing. So computing is both kind of a problem in terms of energy related problem, and computing also is one which is providing the solution in a lot of cases. So energy and power challenges, normally when we think about it, we associate them with, like when we say power management or energy management, the first thing which comes to mind is about battery operated small devices. And that certainly is one very broad category of things where it does matter. But a lot of our other systems, even big systems, have the same issue. So this energy management is a problem at systems of all scales. Those of you who were in today's e-seminar, you heard Professor Markovic talk about stuff which is inside the brain, and of course that represents kind of one extreme end. He was talking about how to make analog circuits which are amplifying the neural signals, kind of energy efficient and all. So that's one extreme, and at the other end, we worry about energy and all at national scales, at the grid scale, and things like that. And almost any system in between has the same effect. I think in recent years, things like hybrid and electric vehicles and all have been a big part. Buildings, again, a lot of stuff happening. Buildings have been around for centuries, but just in the past 10-15 years, lots and lots of smart ways of managing HVAC systems and other systems in a building have emerged. So, so both kind of this is an issue both in computing systems themselves as well as these other systems in which computers play an important role. So the question which comes up then is that, is there, I mean, are all of these kind of just point systems with their own unique energy management approach, or is there some common principles that we can sort of derive behind them and then apply across all these systems, perhaps with different parameters. So when it comes to energy, certainly there are many ways you can kind of approach it. So one is just making the physical system better in terms of the energy it consumes to do some amount of work. So essentially lower power hardware. And by lower power hardware, I don't necessarily just mean circuits. It could also be mechanical or chemical or any other part, any other physical aspect of your system, making that intrinsically lower power. And there are long ways to go. So for example, people often do this nowadays, again, past 4 or 5 years, there is this area called neuromorphic computing, which has emerged and has gained a lot of attention. And so neuromorphic computing, anyone knows what it means? Okay, what does the word neuro means? Brain. What's the word morphic means? Anyone? Having the same structure, morphology, right? So neuromorphic, brain-like. So neuromorphic computing in recent years refers to this idea that if we were to design our computer structurally to be like our brains, as opposed to our conventional computers with their execution units and program counters and stuff like that, but instead design them the way the brain is, namely neurons wired together, neurons firing through synapses and then leading to other neurons fire and all, then perhaps we could do better. And there are two motivations usually cited. One is that our brains are very good at doing certain types of problems which our conventional computers are not, and therefore the hope is that neuromorphic computers can solve those problems with similar facility. So for example, pattern recognition, computer vision, those kind of things which our brain excels at relative to our computers or natural language processing, things like that. And the other one is energy. How much power do you think our brain consumes on an average? ballpark. So it's in tens of watts, somewhere in 100 watt range, let's say. Okay. In fact, it's brain consumes a lot of power. It's a muscle. Okay. Our we have seen computers beat humans in many things now, right? I mean, some years ago, the Jeopardy quiz game. Last year, Google AlphaGo beat the Korean Go player, and that was okay. But if you look at a human with, let's say, an order of 10 watt type power versus these were entire data centers or big supercomputers running megawatts of power, okay, or tens of kilowatts of power. So there are long ways for our computers to go when it comes to energy efficiency, at least on these kind of tasks relative to human brains. And therefore, the attractive notion has been that if we were to adopt neuromorphic architectures, then we can achieve similar efficiencies. So variety of ways of getting to the lower power realm. Other directions people have been doing are things like looking at chemical or biological or molecular computing. Okay, so other non-electronic ways of doing computing. I saw a paper just a day or two ago in some other context, work out of Berkeley, where it was the paper title was zero quiescent power, entirely mechanical radio receiver, okay, or some part of a radio receiver. The point is they're using microelectromechanical systems, MEMS, to essentially create the front stage of a radio, which normally the analog circuits consume a fair bit of power on a continual basis. So people are looking for alternative ways of making things more efficient. Improved energy availability. That's the flip perspective, which is let's not bother about making things lower power, consume less power, but maybe we can generate a lot of power and solve the problem that way. Of course, there is a side story there, which is a lot of our energy is dirty. So if we just produce more energy, then we create other problems. So therefore, hopefully, we not only generate more energy, but generate it in a using processes which are themselves clean and then have that energy be transported and be available wherever you want. And the third aspect is be smart about the use of energy. And this is kind of really sitting in the middle. So one of the ways of being smart is really avoid wasting energy. That is, you should consume energy when there is meaningful work to be done. So just to give you an example, for a computer to stay up while I'm away doing nothing, but the CPU is up, display is running and all, is a clear example of wasted energy. Okay, so to detect I'm not there, there's nothing running, shut off the relevant things, right? So this kind of says something about shutting things down when they are not serving any purpose. Better matching supply and demand. I need only 1 watt of power, let's say, but if I insist on supplying 10 watts of power, then the mere act of that power supply being up and running is going to lead to heat dissipation and things like that. So a lot of energy is going to be wasted there. So this should be a good match between the two. And then finally, and this is in some senses a lot of what we hope to cover in the course, is to leverage smartness. That is, it's ultimately deep down, this is a control system of sorts, right? We are continually seeing what things need to be done, what power would they consume, and then try to make sure that the energy production and consumption is matched. Oftentimes, consumption can be shifted. So instead of running a task now or running it here, I can run it in future or run it at a different place. So tasks can be shifted and energy can be moved around. So you really are trying to kind of match these two processes. And to make that happen, you basically have to rely on algorithms to do it. So that's what energy management comes out to be. So it involves computation in itself, communication, sensing, control, user engagement, sort of feedback from the user, stuff like that, policies from the user. So very trivially, for example, computers often have usually have some sort of a power sort of preferences control thing where you can set put my disk to sleep or display to sleep after so much idle time, things like that. Those are all indications I'm giving to the computer system about my preferences. Uh, Electric vehicles have similar kind of things. Your home has similar kind of stuff now. So for example, in thermostat, we can say set cycles of different types, or if you have a newer thermostat like the smarter ones, they have sensors and they detect when no one is at home or when you are approaching home, and then they activate, deactivate the HVAC based upon that. So sensing, control algorithms, they kind of come together to create a smarter way of managing or matching these two things. So, so these are kind of three things: lower power hardware, improved energy availability, and smarter use of energy. What we'll do early on is we'll spend some time on the first two also, because it's important to understand what you're dealing with before kind of attempting to manage that. So we are going to cover, at least try to develop some sort of abstract model of hardware, which we can then use to for purposes of management. But having said that, the main focus really is on the last part. Okay, so when it comes to so under this broad umbrella of energy, there are very many different objectives with which we come to. So so different concerns. So sometimes we care about energy because energy supply is limited, and the classic case are our mobile devices or battery operated devices, where because batteries have finite energy capacity, so we want to make sure that we are able to sort of cope with this thing. Now, what is a reasonable goal out there? So in a battery operated device like our smartphone, um, is the right objective having least amount of power consumed by the hardware plus software, or do you think it's something else? So let's say you're designing these things. What would your optimization objective be? Yeah.
You also need to minimize heat because you can't just have something that's efficient.
Fair point. So in fact, some studies have shown that given how small we want our phones to be, that affects their dissipation capacity, and that limits. So clearly, one takeaway from your point is that power consumption has to be less than what can be safely sustained by that volume. Okay.
You also need to make sure the performance is not affected when you're trying to optimize power.
Great point, because obviously I can optimize power by doing nothing, and that's not going to help much, right? So clearly there is some performability requirement, right? Performance requirement, which I have to meet to keep the users happy. Unfortunately, in many cases, some cases it's like more the merrier, so that makes things harder. But you're absolutely right. So performance has to be met. Let's say we do that also. Still, is the right goal? What's the what do we want then out of this? Okay, so what other factors come into play?
Cost, the actual devices.
Okay, cost is there, sure, grant you. But I'm looking something which you would be worried on a more regular. Let's say the phone was free. So now what?
It just needs to last long enough to the next charge cycle.
Exactly. So that's what I was looking for. Remember, the goal in itself is not least power. Who cares about least power beyond a certain point, right? I mean, so in some senses, there is a natural recharge cycle that exists in an application. In smartphone, it's quite likely a nightly recharge, but that's not necessarily true for every thing, right? I mean, if it's an implantable, then it probably better be a few years, because it requires opening up the individual. So there is a operating time which exists, and more generally, I have an energy replenishment process, recharging or solar energy or whatever, and my consumption process. And what I want to make sure is that it never happens that the user needs to do something or the system needs to do something and I'm out of energy, right? I mean, that's really my goal. I want to manage the process. So it really, so while one way of, well, sort of minimizing power is a good proxy, but really what you are seeking to do is that availability of the system should never suffer. And now you are subject to that, you're kind of minimizing availability and of course other things that kind of came up in the discussion, safe operation and good performance. In many cases, we do suffer from intermittent or uncertain energy supply. So this comes at, again, in systems of all scales. In some systems, we now rely on things like solar energy and other light energy and things like that. And in that case, clearly there is a intermittency in the supply, and of course our phones when they are plugged in and all. In many cases, these are to some extent predictable, right? I mean, if I have a solar powered something, then I can begin to say something about availability of light from sun or artificial sources that happens in that deployment. Likewise, if if it's my smartphone, people have done studies now which have tried to show and attempt to predict the recharging behavior of individuals, and it turns out that individuals fall into some very distinct bins. There are people who let their phone get to like 5%, it's beeping, plug me in, and only then they plug it in. And then there are people, and I fall into that category, who wherever I see an outlet, I'll plug it in. So whenever I'm in my car, I kind of have it plugged in. So we kind of just never let it, out of fear, never let it fall below some comfort level. And there are people in the middle. And also, you can predict to some extent where I would recharge. Perhaps when I'm headed home versus or work, but not if I'm headed to a restaurant. So there are these kind of different things. So location-based prediction you could do and all. And likewise, the other settings. If I have a solar panel at home, together with, let's say, a battery power pack at home, and nowadays electric supply often depends, the cost depends upon time of day. So if tomorrow is going to be not sunny, so cloudy, sun would be out and all, perhaps the system should be smart enough and then sort of consume extra energy at night, store it in the battery, so that, because at night electricity tends to be cheaper, and then work with it. So predicting energy availability can play an important role in many cases. Third reason, peak power limits on the supply. So this is not something normally we kind of think of, but any power supply and source of power tends to have a limit on what's the peak rate at which it can supply the power to you. And the reason this matters is because violation of these cost. So for example, if I have a battery and if the battery is rated at a particular current value, if you suck more current out of it, it will reduce the efficiency a lot. In a later lecture, we are going to talk about batteries in more depth, but what you would see is that when we say a battery has so many joules of energy, it is at a particular rated current. If you draw at a higher value, then the capacity goes down. So you get less out of the battery. Or likewise, if you are drawing electricity from the grid, from the power utility, then if you have so there's going to be a rating. Your electric panel is going to have a rating 200 amp, 100 amp, whatever it is. And if you draw more than that, it's going to cause problems. But that apart, when you provision a particular power supply, then that's an upfront cost you are putting in. That is, if I were to say that my peak demand is going to be for my home, let's say 200 amp, then we have to put a cable and a meter and everything capable of sustaining that 200 amp. And that's a infrastructure cost you have to do. So many utilities, when they supply stuff, electricity to commercial usage, they charge you for both uh, watts you consume, the energy you consume, as well as the peak current you draw. And even if for a tiny amount in the month you draw a large peak current, your overall monthly rate goes up. And there's a close related reason to it. So those of you who are electrical engineers, anyone knows the concept of real power versus apparent power?
Um, real. It's something to do with storing the energy.
It does.
There's usually some capacitor.
Yeah, so, or power factor, anyone heard of that term, power factor? Okay, what does that refer to? So our electric systems are AC systems, right? Your electric voltage, current are both um, sine waves or cosine waves. Okay. Depending upon the load in your at your home, the current waveform and the voltage waveform can be entirely in phase. That means these are two sine waves whose peaks are aligned, or they could be entirely out of phase, which is when one has a peak, the other has a zero, or vice versa, they're out of phase, or somewhere in between. And that depends upon whether the load at your home is resistive, like a tungsten good old light bulb, or whether it is non-resistive, like for example, a laptop power supply and something like that. And what that means is that if my load has more of a inductance capacitance kind of behavior, then what happens is that will be out of phase, those two things, and then what happens in one part of the cycle I take energy, in another part of the cycle I dump out energy. So I'm not drawing any real power. If you have go back to your kind of physics, if I have a inductance or a capacitance, then I'm not actually dissipating any heat. If I have a pure inductance or a pure capacitance, all I'm doing is I'm moving energy around. So poor electric utility, it still has to create that cable with sufficient thickness and all to be able to move the current to me and move the current out. But I'm not consuming any energy, right? So obviously they cannot survive economically with that kind of model. On the other hand, if I have resistive, then of course there is heat dissipation taking place and they can charge for it. So they always charge for the real power, the watts consumed. But they also got to charge somehow for this process of moving the current in and out. And that's why the peak current does matter. And this becomes a big issue when your loads are non-resistive or the power factor becomes zero, if my math is right. Okay, heads over zero. It's cosine of the phase difference. Okay. So long story short, this peak power limits come for a variety of reasons, and they are actually beginning to get priced in. And you can also buy these things called power factor correctors to kind of make your load look sort of more appropriate, well behaved also. So this concept of peak pricing has kicked in. That is particularly for industrial scale usages, or like when UCLA subscribes to energy and all, they probably would have as part of their contract something about the peak current. So if peak comes at a high cost, because peak means that the whole infrastructure has to be designed to cope with that peak, which may last for a very small amount of time. Thermal considerations. That's another aspect, and which was alluded to earlier, which is when loads consume energy, whether the load is a computer or a building, then it produces heat, and that heat in turn has an adverse impact. So when a computer chip produces heat, obviously that temperature will go up if you are unable to remove all that heat. And of course, removing heat takes time. It's dictated by the thermal coefficient of the materials involved. What happens? What do you think happens if the temperature goes up?
Resistance goes up, so you use more heat.
Say it again.
The resistance of the chip also increases, so you use
Yeah, okay, so, or more precise, you're right. So, I'll not comment on the first part, but the conclusion, yes, it consumes more energy. So, essentially, what happens is that as temperature goes up, leakage through the diodes in the circuits begin to go up, so they begin to kind of essentially more current flowing between power supply and ground in effect. So it's kind of intuitively what you're saying. And end effect of all of that is that you get into this kind of a vicious loop. You consume more energy, temperature goes up more, you consume even more energy, and you get into something called thermal runaway cycles. And then temperature can go up very rapidly and destroy the chip, okay, or do other. So which is why modern chips also have thermal protections and all. In many devices, you might see things like it has gotten too hot and it shuts down. So that's the thermal protection kicking in. And it also affects reliability and like. And then the final one is sustainability related considerations. These matter. I mean, this is certainly getting into perhaps a bit of political domain as well, but at least fair part of scientific community believes that uh, sort of fossil fuel emissions and all uh, are a problem, and therefore that impact, that is one way to affect the global warming and all, is to also reduce energy consumption. So there's one way is to kind of change the mix of energy production away from fossil fuels, but the other is to also just generally be more energy conserving. So carbon footprint, environmental impact, use of non-renewables, which also has its own considerations. But many other systems also have issues. Like for example, take electric vehicles. They rely on big lithium battery packs, and those lithium battery packs have to be disposed of at the end, and their disposal adds to additional complexity. Or take nuclear reactors, very clean, but when the spent fuel rods have to be disposed, they become a problem. So unfortunately, it's always a matter of trade-offs in engineering, and you would find that different technologies kind of end up being in different bins, and things change over time. Like coal is dirty, but then there is also stuff like carbon sequestration and sort of ways of taking the carbon emission and sort of essentially handling it properly. So it's a change in technology mix, but all said and done, there is this issue that our the environment of our planet, sort of the effect on that needs to be considered. Any other things that you guys think of that I've missed in this discussion? Just curious. I mean, you are from many other different countries, so the perspective I'm giving is very much the American one. But any? I remember I was 2-3 years ago. I was giving a talk in India, and along the lines of building energy management and all, and a student said, raised his hands, sir, but you guys waste a lot of energy. We do not, or something along those lines. And there's probably some truth to it. Okay, I mean, we don't think twice about leaving lights on and all out here. Whereas I recall growing up in India, my mom will scream at me if I left light on in a room that I was not in. So I think views towards energy are often driven by whatever the economic climate that exists. But that apart, I mean, what other kind of energy related issues have you guys seen in sort of other places? Just curious. Sandeep? Thoughts?
I have seen like in real-time monitoring stations, especially that are movable stations, this is a problem. Like in water system, say the battery runs out,
Mm-hmm.
you are there for some events which you want to measure, and that's a big problem.
Okay. One other thing I noticed in India, because I had a collaborative project there, so it was kind of a couple of things that were interesting to me. One was because the power grid there is a bit flaky, or considerably flaky. So what happens is that when the power supply goes out, then to keep working, so they have these generators which run on diesel, I believe. Okay, they kick in. So you're sitting in a meeting in a fancy company and suddenly power goes out and then this generator kicks in. The problem is those generators are immensely polluting. So lack of reliability in the grid translates into kind of thing. So there's often this tension that kicks in. The other one, which I've actually seen in many other places also, this nexus between energy and water that exists. So, and this is actually very true in Southern California also. Our water supply, where does our water come from? Okay, leaving recent rains aside, where do you think our water supply in LA comes from for the most part? Anyone? Come on, take a guess. And we don't have massive rivers here in LA, right? I mean, or snowpack, so it must be coming from someplace.
Just gonna throw out there Colorado.
So we get from Colorado River, that's one. We also always keep an eye on how much snow is on Sierras because a lot of our water comes from Northern California through this thing called California Aqueduct, which is this massive canal which runs from Northern California to Southern California, along the way supplying water to various agricultural things and all. Then some of our water comes from groundwater, so we extract stuff, but there's very little of that remaining. And then the new one lately is that in San Diego, if you ever drive around San Diego, now closer to San Diego, you'll see this big desalination plant which is coming in. The private company called Neptune, which is creating it, and desalination, basically taking the Pacific water and creating water out of it. And actually, the fifth one is something called brackish water recycle, which is often called as P2 water or whatever. Like I mean, our sewage and all being recycled back into our water supply. Many of these, almost all of these processes here are extremely energy intensive. Water supply coming from Northern California has to be moved. Desalination, extremely energy intensive. Brackish water thing, you have to sort of recycle the water in effect, extremely energy intensive. All of these things, what it means is that in essentially when you are using water or wasting water or whatever, you are actually also wasting an immense amount of energy. In California, a very large fraction, I think it's 30% of all energy and roughly half of all electricity is for water related usage. In most cities in the on an average in a city in the US, the largest electricity consumer is the water utility, accounting for 30 to 40% of energy usage. Okay, so this is something that we don't see directly. Another number which I saw someplace was the following, that if you take your average tap, turn it on, leave it on for 5 minutes, the energy you have consumed would have sufficed to get a 60-watt light bulb on for 14 hours. Okay, so when you see it this way, you kind of see that we often consume energy through very hidden or indirect means, non-obvious means. So many a times savings in energy can come from saving in some other dimension, saving some other way. Like for example, getting people to use less water may actually be more effective way of saving energy in Southern California and many other parts of the world, India, Australia, all these places, or Saudi Arabia, these kind of places where water is particularly energy intense. Computers. And more generally, the concept of vampire power. Anyone heard of that term? Vampire power. So vampire power refers to the fact that we have tons of electronic devices and electrical devices, and they're never quite fully off. They're consuming teeny bits of power, and when aggregated over tens of devices per household and hundreds of millions of households, they add up to a lot. So this little energy which is sucked and wasted doing nothing becomes a problem. And one of the quote I have in a later slide is that to make things energy efficient, it's also very important to do nothing very well also. And let me clarify that. When your system is idle, doing no work, it should ideally consume zero power. But they don't, partly because of poor design and partly also because we want responsiveness. We want our computer to wake up the moment we hit the key. So that comes at a cost. Something has to be vigilant, and that is true for many other systems also. So so this trade-off, these trade-offs play out in kind of complicated ways, as kind of we'll see. Okay, any other thoughts? Okay, so let's move on. So there is, unlike other sticking to computing systems, most elements of our computing systems have been improving exponentially through various exponential laws, communication bandwidth, computing ability, memory size, these kind of things. But unfortunately, not power sources. So power sources, like, and by that what I mean is battery energy density, for example, our ability to store, it's been moving historically at single-digit percentage points, whereas Moore's law was 50% to 80% per year or more. So very different growth rates on these energy sources. This is another example. So our current dominating battery chemistry is the so-called lithium-ion battery, and that's pretty much what you would find in most things, your laptops and smartphones and your electric vehicles and stuff like that. Battery chemistries change relatively infrequently. Lithium-ion and related lithium chemistries have been around for a number of years now. They have improved in a variety of ways. Samsung Note 7 notwithstanding, but batteries have improved a lot in a variety of ways. They used to be one big way. If you go back 10 years, you would see is that the number of times you can recharge battery used to be 100, 150 or so. Now it's 1,000 times or so. Okay, so which is why manufacturers are now able to seal in the battery, non-replaceable batteries, because your phone will become obsolete before the battery runs out of charging cycles. But they run into problems. Apple, for example, did a recall of iPhone 6s battery a couple of months ago because some of them had manufacturing defect, and I already referred to the Samsung one. So it's a tricky thing, but nevertheless, they improve relatively basically compared to other aspects of our computing systems. Solar photovoltaic panels, which is the other part. So this is the generating part, the clean generation. They have also been improving quite a lot. Some of it is driven by market forces. So like, for example, cheap solar panels coming in from China, because China moved big way into solar industry, so that drove down the panels here. So net effect was that the solar panel installation cost here sort of went down dramatically. So solar panels have improved a lot, but not so much in efficiency. So the price certainly has improved quite a bit, but efficiency, by efficiency I mean the efficiency with which they translate a given amount of solar flux into electricity, that has not improved that rapidly, because that requires more basic advances in the underlying material and all, the equivalent of battery chemistry. Heat dissipation, we already kind of talked about it, but essentially when electronics dissipate heat or systems dissipate heat, then that heat needs to be removed, and failure to remove that heat affects various aspects of the system. So we already talked about the damage they can cause. There's a nice picture. But to remove the heat requires in itself issues. So you'll either have a fan, or you'll need a heat sink, or you'll need some other heat removal process like coolant or something like that. And all of that will either cause cost, or they themselves may require energy, or may create other things, like take fans, for example. One of the issues in our computing systems has been that that fans create noise, and in many settings that's not acceptable. And likewise, fans become a failure point because they're intrinsically mechanical. So their bearings may fail or stuff like that. So all of these things end up having implications on reduced reliability, reduced performance. If you are unable to remove the heat, then you have to slow the computer down. Rapid aging. So if you continue to run the circuits at higher temperature, but not so high as to burn out, but high enough, then they age more rapidly. And by aging, I mean literally their material structure begins to degrade, so the performance of the circuit goes down over time. And thermal runaway, which is what this picture is about. So many years ago, the slide is a dozen or so years ago, Intel had this slide or some version of the slide where they kind of showed how the temperature at the heart of the chip, their i86 processors was going up. So across various generations they were showing, and one of the things they were showing was that look, if nothing was done, then by the time you would hit Pentium 5 or so, you would be at a nuclear reactor core-like temperature. Of course, you can't sustain that. Everything will melt at that level. So something changed. And one thing, if you look back at the following, so what's the peak frequency that you currently encounter for processors in our typical laptop, desktops, and all? Ballpark. What number is that? Like when you buy a laptop, what kind of frequencies do you typically see nowadays? Huh? 3 to 4, 3.3, 3.5, somewhere in that range. If you're really high-end gamer type stuff, maybe you'll get 4. Okay. It was pretty much the same number 10 years ago, or even 12 years ago. Nothing has changed really on that front. And the reason was this, exactly that, I mean, if you keep increasing frequency, temperature will keep going up. So something else changed. What changed? I mean, obviously our computers. Huh? No, feature size is technology. Something else changed to keep the same speed, right? I mean, so you're right that the feature size continues to shrink, but we are not leveraging that feature size to improve the frequency. We are leveraging that feature size to improve in some other dimension of the architecture. Huh? More cores, right? I mean, our chips nowadays have 12 cores or 16 cores and stuff like that, or more precisely, parallelism. Okay, parallelism is what came to the rescue. So and parallelism takes many different things. There is something called hyperthreading, and then of course multiple cores, and deeper pipelines, and superscalar, and blah blah blah, whole bunch of stuff. But upshot was that we made use of these additional our ability to pack more devices because of reduced feature size by improving architectural parallelism so that we can still benefit speed-wise. And of course, it also meant that our programming abstractions had to change, our operating systems had to become better at making use of those things and all, but we could not keep increasing the frequency because this thing kind of put a stop to it. In fact, feature size reduction made matters even, the reason this thing is getting worse is precisely because of feature size reduction. As feature size is reduced, same number of transistors, which are switching still as frequently, are getting packed into a even smaller area. So more transistors, smaller area. Moreover, if I scale the wires in the same manner, so if you recall your physics, the cross section of a wire affects its resistance or resistivity, right? And if I shrink it down, then the resistivity will go up, the resistance for the same length of wire will go up, and therefore power consumption will go up. So upshot is that if you just blindly scale, you're actually making this problem worse in multiple manner, and soon sort of that watts per square meter or whatever, power per unit area just skyrockets. And so you have to give some place up, and one of the ways you give that one up is you don't scale interconnects the same way. That's one part, so your wires still remain good. But the other part also, so wires don't scale as rapidly as devices, transistors do. But other part is we stop scaling the frequency, basically. Okay. And the third thing, even with all of that, we still have a problem. So one term that you would see referred to is something called dark silicon. So it comes from analogy with the dark energy in physics. So what dark silicon refers to is the fact that we can put a lot of stuff on our chips, but not everything we can put on our chips today, we can keep running simultaneously. And the reason is, if we run it all simultaneously, we again run into the same temperature issue. So dark silicon basically refers to the fact that a large amount of our silicon is forced to remain idle, because if we were to run it, then we will have a meltdown. So then it again has architectural implications, because what it means is, if I cannot keep everything on the silicon running simultaneously, then there is no point in having n cores, because I can never make use of those n identical cores, because I can never keep those n identical cores running at the same time. So perhaps I can do something differently. And one of the things that happened in recent years is this notion of cores which are not identical. Specialized cores. I will put a bigger GPU, I'll have some other specialized processors which I may not need all the time. But when I do, I run it only at those times. So I don't keep, so now essentially I have this dead silicon which I can use in this particular manner, or dark silicon which I can use in this manner. So that's the story behind this. So shrinking silicon, while obviously has been a big boon, has been a very complicated story which has happened sort of behind that. You see this story play out in many different ways in many parts of computing systems. So it's a bit of an older slide, but it's basically showing that in data centers they face the same issue. In data centers, you have these blade computers, as they're called. They're kind of packed into very dense racks, but the heat has to go someplace. And so data centers are designed very carefully with airflows, HVACs and stuff like that to kind of make things happen. But upshot all of this is that the heat load footprint, so whatever heat that I have to remove from a particular part of the data center, has also been going up. And by the way, it's an exponential scale on the vertical side. Okay, so again, sort of huge problems there as well. So data centers, one way of thinking about them is, it's data centers are those racks of computers together with a cooling system, the HVAC system, designed together, and by the way, with a power supply also designed together. So it's a very complicated system. A lot of attention paid to them by companies like Google's and Facebook's and all, because they have a lot at stake there. And the dollar cost of energy also matters, and a related part is not simply energy you consume, but also the dollar cost of energy you spend to remove the energy that was being dissipated. Okay, so the heating and cooling cost which comes up. So what this is showing is, again, sort of slide is a bit old, but the trends have been very similar. So what's showing is, in yellow, what you have is the percentage of the cost which goes towards the actual computer, and the cyan color is the percentage of the cost which goes towards the cooling system. And the message out here is that a bigger and bigger chunk of the overall cost actually goes into managing the cooling part in these data centers. That's been the big. And then finally, the last point I had a few slides ago, the sustainability story. So there's been a lot of attention paid to this part in recent years as sort of awareness of these issues has kicked in. But kind of the main thing is that our planet is able to sustain energy expenditure and all at a certain level, and beyond which it seems to be having some detrimental effects. So this nexus between energy and, I guess, very broadly environmental sustainability is driving a lot of policy decisions. And I guess in recent times, this Paris Accord, for example, and all these are all efforts in sort of that direction. Main thing really is that energy consumption is growing very, very rapidly. So this is how it looked like. Okay, it's not today, it's like 2012 or so, but this is what the projection is. And the main point, as you would expect, is that as parts of the world which were not as well off are getting all the modern amenities, you kind of begin to see things coming up. One of the things that governments like to do is this detailed analysis of the energy flow that is happening through our society. So this is true for US, and what you see out here is on the left are the different sources of energy America relies on. So you'll see petroleum out here at 40%, natural gas at 22%, coal at 22%, nuclear at 8%, solar, wind. And again, this is, I think, 2013, 2012, something like that. Well, the point is, every country would have some mix like that. In Europe and all, nuclear is a lot more, and coal less so, and so on and so forth. In India, for example, I was reading, coal is 80% of the electricity, so it's a much bigger number. Within the US, state to state, this changes. So I was looking at a nice thing where is electric car, a plug-in electric like Tesla or Volt and all, is it better than ICE car, internal combustion engine? And the answer is it kind of depends on where you live. If you live in Louisiana or Kansas or Colorado, where the electricity is generated dominantly by coal, then you may actually be better off driving a ICE, which is low emission, than driving an electric vehicle. Okay, so whereas in California, where much of our electricity comes from natural gas, the story is reversed. Okay, so things can often get more complicated if you do a second level analysis as opposed to just going by the high level way. So all these energy supplies flow into a system, in this case our whole nation, and then you have a variety of different outputs. So you have vehicles, industrial usage, commercial usage, residential usage, and so on and so forth, and electricity generation, which feeds in. So it's a complicated story, and not all sources are similar in terms of their impact on environment and their cost and all, and likewise not all uses are similar in terms of their economic impact and all. So a lot of work that people in economics and all who work in these topics, they kind of analyze these kind of things and all in to look at what the overall impact is. So what in computer science has been happening in the past dozen years or so is really this recognition that we have these dual opportunities. One is that our computing infrastructure itself can be helped considerably when it comes to energy, particularly with data centers and more powerful computers, as well as our phones and stuff like that. So use energy efficiently when operating, use little energy when idle, use sources of energy that are clean and sustainable, use less energy in manufacturing, and produce less satisfied products. And the second story, which has been playing out, is using computing and communication systems and machine learning and sensors and all those kind of things to make other systems better. So make cars, homes, offices, factories, and all more green or better energy usage, enable use of clean and renewable sources of energy. So this point is worth spending a little bit of time over. So solar panels, wind turbines, and all these are around, but we still don't see them becoming a bigger factor in our electrical grid. Now, part of it is obviously the cost of the sources themselves, solar panels and all, but a lot of them have improved quite a bit. So the sheer cost of the source themselves have become quite decent. But there are a couple of other ancillary factors which have not come along equivalently along the way. And one of the big ones is the following, that most of these so-called, most of these clean sources, so basically solar and wind, they are not something which we can turn on and off. Unlike an electrical generator, which I can start and it will generate electricity and I can stop feeding fuel to it and it'll stop. Wind and solar are not like that. They're not under our control. So they are intrinsically unpredictable. They're power supplies which we do not control to turn on and off on demand. At the same time, population, our society consumes energy at it's a hot day, I'm going to turn things on, there's a game going on, all the TV come on. So the demand side happens with its own process. Now, if we had a fossil fuel based generator, then if the demand was going up, we will basically make more generators come up. But with renewables, we do not have that luxury. I cannot tell the sun come up now, right? So what can we do in this setting where now we suddenly have a big part of our power portfolio which is not compliant, in the sense it's not necessarily happening at the same time in the demand side. So what do you think are the technological solutions for that workout? Let's say you're designing a grid where most of energy was coming from these renewables, solar and wind. So, but still to keep your customers happy, you would need to do something. So how would you cover this gap? Huh? You need to store it. Okay, so storage, what are the ways we can store electricity or energy? So batteries is one, obviously. The problem is making batteries at grid scale is immensely costly. So there are other ways you have to figure out to store, and also, so these so-called grid scale energy storage is something which a lot of investment has been happening in recent years. Things range from when I have excess energy, I'm going to pump water up and then sort of use a water turbine to kind of generate electricity when I need it. Heat up a metal, so store it in form of heat, and all. So all those kind of things. I think now we are reaching a stage where, because of EVs, the battery industry has gotten a big boost, that we are beginning to see larger scale batteries beginning to come up. So if you go to Tesla's website, Tesla, besides selling the cars, also sells batteries. They sell two kind of battery packs. One are the so-called power walls, which you can buy for home. I priced it, and so basically for my home with $11,000, they tell me that I can get a battery pack which would supply all the energy needs of my home for a day, 24 hours. Okay, so that's pretty steep still. Or you could be a company and buy their other product, which is a bigger battery pack, and the pricing there starts out with a few $100,000. So if you're a Google and all, you can buy these big, massive installation of batteries as backups and whatnot, and they are priced into, starting from there, they go into many millions of dollars. Last year, here in Simi Valley, there was this episode that some of you might recall, or those of you who were here at least, that there was a leak from a natural gas reservoir, and that was resulting in that methane being burnt, and that went on for weeks, and apparently California, more carbon emissions were done during that time than California does over the entire year, those kind of numbers and all. So when they finally decided to shut it down, they replaced, so the idea behind that natural reservoir, that was the emergency supply. So they are replacing it by a battery pack, a large battery pack, for which the contract went to Tesla, and it's a $30 million lithium-ion battery pack. Okay, so that's sufficient to supply energy for a small town for a day, basically, kind of number. So battery technology is sort of driving, is certainly a huge part of it. So that's one way we can do it, right? So we can store energy when there is excess and do it. In the absence of that, because these batteries are still expensive, there is something else you could do. So I cannot affect generation because it's not under my control. I cannot store. So what does it leave? Consumption. So can you change consumption? So what does changing consumption mean? Changing people's behavior, right? When they do something, and changing policies, right? I mean, so stuff like that. To some extent, that is influenceable. How do we influence behavior? What's the best way?
You change the time,
Huh?
like an hour early, or
Yeah, but how do I, if I want to, money, exactly, money. Yeah. So dollars. So basically, you price electricity differently, price energy differently, right? So you basically, I want to make people do their laundries and charge their EVs and run their pool motors at night, make electricity cheaper then. So it's called time of use pricing. Okay, now it works, but oftentimes it doesn't. Oftentimes there is excess energy in the grid. Now, when that excess energy happens in the grid, now one option is you can say, okay, I'm going to, since the grid is still not 100% solar, it's far from it, so I still have regular generators and all, so I can turn them down, I can turn them off, but that is very disruptive. So at those times, I want people to consume energy, so I'm going to lower the energy cost. In fact, sometimes you may have to lower it so much that it becomes negative. That is, the utility will pay you for you to consume energy because it's costlier for them to shut off the generators. Okay, and this happens quite often. It's happened a lot in Europe where there's a continental level sort of market. So energy pricing, and this is something called demand response. The idea being that I'm going to give you price signals, I as in the utility, and the idea is you're going to change your behavior accordingly. That's what economic theory suggests. And therefore, this demand response in real time is something which happens in California. Any entity which is big enough, I think like 50,000 kilowatt hour, or some 50 kilowatt or higher type loads, they are required to have this demand response. What it means is there is a communication link, there is a protocol, a message comes to your system saying, yeah, this is the price, and you can adapt to it. Or they may even say, shut it down, things like that. So those kind of things happen. So with all of that, the idea is by managing the load, by managing the storage, and also finally by predicting things. So for example, if I know that tomorrow is going to be cloudy versus um, sunny, or that tomorrow there is a game and therefore there will be more people staying at home and more ACs running, kind of predict this thing, and then on a rolling basis you say how much generation I should be doing, and this is machine learning coming into play. So all of these things come together to make sort of clean renewable energy possible, and that's still an ongoing process. And then finally, efficient operation. I already talked about water and how it connects back to energy, and there's a lot of other stuff. So what we'll do is we'll kind of explore both these dimensions, the latter one towards the end of the course, and kind of for now sort of focus more on making computers themselves greener. So looking at computers themselves, so I talked about how data centers are a big part of the planetary level energy consumption and all, and that holds true more broadly for uh, information technology as well. So people have sought to quantify these things, like how much. So ICT refers for the entire sort of information communication technology infrastructure. How much does it account for of the carbon footprint? So the emissions that are going on. This is not energy consumption, but the emissions that are going on. What is the split between these? So this pie chart is basically showing that data centers are roughly 20%, all these kind of mobile phones and stuff like that, and associated telecom infrastructure a quarter, and then all sort of computing equipment and office equipment and all accounts for roughly 55 to 60%. In buildings, the traditional wisdom often was that buildings are dominated by lighting and HVAC. But in modern office buildings, or particularly information technology intense buildings, the computers become a big power. So this is data from a study that was done at UC San Diego, and what they showed was that PCs and servers constitute roughly 70% of the load. Okay, so they're basically kind of it's faint out here, but this purple color is, for example, lighting. There are mechanical loads which come and go based upon consumption, but the problem with office equipment, PCs and servers and all this, it stays on all the time. We do not make use of all the facilities that exist to shut things down. So for example, my lab has a whole bunch of servers. Irrespective of whatever we are doing, they're always running. Okay, in fact, most of the time we are doing nothing there. And likewise, our desktop computers and these kind of things remain on a lot of times, even when we are not using them. Now, part of the issue is, in many cases, we are aware of that fact, we want to do it, but perhaps the software is not appropriate design. But there's another reason which motivates us to leave these things running all the time. And that motivation is that when we need it, we want to be able to access it immediately. Or for example, oftentimes nowadays we use our computers at home for doing Skype and stuff like that, where someone else is trying to reach us. And if our computer was off or shut down, then that may not happen. So we might miss these kind of conversations. So one of the reasons which also drives people to kind of not shut things down is this always on or always accessible thing that we need, that we want the service to be always there, and therefore we leave it on. So I guess one of the things that computers still don't do as well as they should, although they have improved considerably, is giving us the simultaneous illusion of being available but still being off. That is, if I have a service that I have a Skype call, FaceTime call, whatever coming in, it should still come through. But if I'm not there, not running anything else, it should sort of go down. And over the past 5 years, 10 years, a lot of efforts which have gone on towards making this kind of thing happen. One dimension where they certainly have gone very good now is instantly on. Okay, so nowadays, I mean, we are very used to the idea that I click on my phone or my iPad and it just comes on immediately. It didn't used to be like that. It used to be that when my PC would go on hibernate, I will click on it and then wait and wait and wait, and before it will come up. So things have certainly improved quite a bit there. Nowadays, we just flip open the laptop and it's ready for me to sort of take my click. So a lot of things happen. What all do you think made that magic happen? Like, why was it that 10, 12 years ago, things from wake up my laptop would take a lot of time, and nowadays it doesn't? What changed? Okay, maybe some of you are too young to have faced those laptops also, so you're excused, but yeah.
I'm thinking it's just quicker memory these days, so storing things to memory and loading them back up is quicker.
You're kind of in the right territory, so it's not that the memory is quicker. Huh? No, so the point is it's no longer the disk. So let me explain, okay? So I have to store that state someplace, obviously, right? And it has to be stored in a place where, while I am powered off or in some sort of ultra low power state, the state is still remembered. So what kind of memories do we have? We have disk and we have DRAMs, right? So disks are certainly persistent. They retain the data when they are powered off, right? DRAMs, it used to be that if they did, they would consume a lot of power. So it was not realistic for us to store stuff in the DRAM because they were big enough, so they could store the amount of data. That wasn't the issue. But they were not big enough, they were not low power enough that I can store the data and then do it for a long time. What changed was the emergence of these DRAMs, which could be put into a low voltage mode so that they can retain the data and do it for weeks. Okay, and that enabled these new generation of sleep modes where essentially I can have the man mode. So that was one biggie. The other big thing that changed was the mindset in the operating systems. So it used to be that when you would go into this kind of hibernation mode, then when you would wake up, particularly if you were on a Linux computer where you could see everything going on, you would see that essentially a whole reboot process was taking place. It was booting from scratch, it was probing the USB bus, what all devices are there, everything was going. It had two implications. You're rebooting from scratch, you're not benefiting from anything about the prior state. And the other thing is you were doing all this sort of probing of hardware devices and all kind of every time you're waking up. So operating system people also got optimized this thing. So they optimized the reboot process. Apple in particular for their iOS and all, they kind of a lot of stuff which then, since then, a lot of other devices began to follow also. So those of you who have kind of used PCs and Macs both, I mean, you probably noticed Apple computers were always pretty good at this rapid wake-up, whereas Windows took some time to catch on to that. So two things happened there. They optimized the boot up time. So what used to be minutes is now seconds. If you look at Linux boot up time and all, considerably sped up. And the other thing is that they began to maintain, make use of the state information about what devices are connected or what were not connected. So they remembered a lot of stuff. So between a combination of these things, that DRAMs became lower power while still retaining state, and the OSs got optimized. We basically got have improved considerably on that division, but still not fully there. Like I said, we often deliberately leave things on because we are expecting something incoming, and that's always a problem. We don't know how to handle that very well. I have some slides here which kind of go over the carbon emission kind of a story, which at least a lot of people sort of worry about a fair bit. So it's basically what lot of government agencies and non-profits and all do is they kind of do these projections based upon the trends that we are seeing, and then use those projections to then help drive policy changes and all. So a lot of that kind of work we have been seeing in recent years. And upshot really is that the message which was going out was that ICT industry itself, information technology industry itself, has to optimize its artifacts, computers, data centers, and all for energy, because it's a bigger and bigger footprint of the planetary scale kind of stuff. Okay, I'm going to skip a lot of these things. This is data center. I guess one of the some salient things that you would see out here is, so if you look at this one, 2020, which is roughly more appropriate representation. So what you see, this thing is split into a whole bunch of things. So the entire data center, you could think of, it will have a whole bunch of servers. So these are your real computers, the one which you really care about. Okay? But that's only roughly half the data center. The other half is being consumed by cooling system, power system. So power system consume energy. Why is that? Well, that sounds a little bit weird, right? Power systems consume energy. What's going on? Is anyone else? You must be tired of raising your hands. Yeah.
The power management.
Yeah, but what about it? This is a power supply, right? I mean, huh? The heat, yeah. I mean, wires, right? I mean, they have heat. Everything in the power supply chain has some efficiency factor, right? So the inefficiency is really what you're taking a hit on. So power systems, storage systems, these are your drives and all. These are not really the active computing thing. And then usually there are some additional servers and all to kind of manage everything. The point is that in a typical data center, every joule that you feed in, you also have to feed in, if you were to go by this, a joule to keep the whole infrastructure alive. Okay? Now, a lot has happened out here, so this is not necessarily representative of the best data centers, but you can roughly think of that. I can think of a efficiency, energy efficiency for the whole data center, right? I mean, what's the useful energy, the one which is actually going towards computation versus the rest. And of course, the other part is how efficiently I can do this useful part, right? I mean, the computers themselves here are improving. These are different ways of looking at the same point. So what this is showing is the following: in an entire data center, roughly 40% is the actual IT equipment, and the remaining 60%, so slightly different numbers, power delivery and cooling. Within the IT equipment, the compute was 60%, and rest was storage and communication. And then within the compute, you had CPU, memory, hard drive, power, local power supply, and all. Okay. But the point is, by the time you come at the CPU, it's 8% of the total. Now, this precise number may not necessarily be general, but point is that if you only focus on the energy consumed by the CPU, you're looking at a very tiny part of the overall picture, right? And therefore, and many of these things can have unintended side effects. Like for example, if just looking at this and I were to give you an algorithm, I would say optimize it for energy. And you might say, okay, so I'm only asking you to optimize for CPU energy. Maybe you will replace a compute intensive algorithm by a big table lookup. And that table lookup will improve the CPU energy consumption, but will make worsen the memory and the hard drive, for example. So it's very important when you're optimizing for a particular task to really look at the overall system picture, because it's very easy to offload your load onto someone else. I want to improve Bolter's Hall's energy efficiency. I can mess with engineering 4 or whatever, right? I can basically move all the students from here to E4, increase the workload there, and Bolter Hall will look great. So these kind of work shifting kind of things would be kind of cheating. So likewise, when you're doing a system analysis, it's really important to look at the system honestly in its totality, not just focus on one part. But that's a mistake we often make, and oftentimes we make it deliberately. It used to be that CPUs were a big part of power consumption in certain type of computers, but that's not necessarily always. On our smartphones, what do you think is the biggest consumer? Huh? Display. Yeah. What else? Huh? No. Speakers are very radios. Yeah. So typically the practice is when they quote you, at least in case of Apple for iPhone, when they quote you the lifetime numbers and all, it's assuming a duty cycle rate of percentage usage for these things. For display, the number is 5%. It's assuming that your display is not on for more than 5% of the time. Okay, it's a pretty low number, and that's how these things are portrayed. Because I mean, in fact, that's probably reflective. But the point is, if I suddenly start running something, a math program where it's always on, no, obviously it will. So radio, GPS, these are kind of other. We know how to do this very well. Actually, it's all this other stuff which complicates things a lot. Okay, so the final thing that I want to cover today is this concept of what is called as energy proportional computing. Okay, so what this histogram is showing is the following. This plot is showing the following. This is for servers, but similar concept for all computing devices. So you can define for the CPU a utilization. Utilization is basically what fraction of the time is the CPU busy. So 100% utilization means the CPU is doing something all the time at its full frequency. And 0% means that the CPU is doing nothing. Okay, it's just doing some groundwork or some background work or go-offs. Okay? And what this is showing is what fraction of the time was a typical server is at these levels. So what you see is, occasionally it is very utilized, A lot of times we are here, so there's a peak out here, and a lot of times we are doing nothing. And that's true if you think about it for a lot of our systems, right? I mean, our smartphone, when I touch it, do something with a burst of activity and then silence. Or servers in a data center, some barrage of queries come, it runs, again, nothing for a while. Desktop PC, same thing. And in fact, this part is often very high. And that a computer is truly fully utilized, 100%, is relatively rare. So most of the time, our systems are actually pretty lightly loaded, or is somewhere in the middle. But the problem is we still design for this, because there are occasional times when we need it at this level, at this high level. So we often pay for that peak thing. For example, our cars are designed to whatever at speeds of peak speeds of a typical car sold out here, 140, 155 mph, something in that range. I don't think we have ever driven at that speed, but we still get it because that higher rate car also gives us a higher acceleration. So it buys us that headroom at occasionally when we kind of do need it. It's the same thing with computers. Occasionally they need to sprint. Most of the time they are in a marathon or they're resting. Okay, that's what's happening. So the problem that happens though is now when you look at the energy picture, or rather the power picture. Okay, so again, same utilization. What's happening is that when you look at their power, it looks like this green curve. So yes, power increases as the utilization increases, but it does not go down to zero when we do nothing. This y offset represents the baseline power that we are always consuming just because our system is on, waiting for something to arrive. And the net effect of this is that if I look at energy efficiency, which is utilization over power, that's the red curve, it's basically saying that when we are at high utilization, we have good energy efficiency. When we are at low utilization, we are lousy. In other words, when we are doing nothing, we are doing that nothing extremely badly, because we are doing zero work, but we are consuming that baseline power consumption. So that's the bad part of the story. And this paper, it came out of Google, early days of data centers and all, 2007, and this kind of led into the computing jargon, this kind of term, energy proportional computing. Ideally, what we would like to have is that this green curve should cross at zero. I do nothing, it should consume zero energy power, and as I increase, it should go linearly. Right? That's your holy grail. But systems don't behave like this thing, right? I mean, your car, when it's not moving, just idling, still the engine is on and it's running, right? I mean, at least the baseline of the system. And that's the problem. So I'm going to stop out here. We're going to continue pick up on this thread, but one of the message to take away is that one property we want out of our systems, not just computers, this is true for cars and buildings and whatnot, is this energy proportional behavior. They should do nothing very well also. Okay. So let's pick up the discussion on Wednesday.